Okay, I guess we can start. So hello everyone, my name is César, and I'm a staff software engineer at Shevia. I like climbing and motorcycles, and I have a dog and a cat. And after that introduction, very small one, I'm going to talk about how to design domain models for writing to the database. But in particular, I'm going to refer to a document-based database, so kind of NoSQL database here. So there are a bunch of different ways that you can structure your types, your domain models around this, right? From very simple and super easy, like just use the same types for everything. You have a data class, you have a codex to write and read from the database, and you use that. But that's has very clear limitations, right? So the more usual way to handle this with this kind of databases is you have persistence models. You have your domain types. In the applications, you map them to your persistent model, and then you use this persistent model to define encoders and decoders to write to the database and handle different logic around how you control the life cycle and logic of storing and retrieving data, right? What I'm going to discuss today is like taking a step further, which is separating these models into two models, two different ones. One only for writing and one only for reading, or maybe even more for reading, but making the distinction between the ones that you use to write to the database and the one you use to read. And this is very influenced by the fact that we're going to have like a different path for the data to be written into the database and the data to be read from the database. We're going to talk about a system where we have a data ingestion pipeline of events, and these are immutable events, and we don't control, we don't own the data. So in the end, the applications are only reading from the database, not writing, right? So the outline of the talk is going to be like, I'm going to talk about the motivation for why would you want to split these models instead of using like a more traditional pattern of the persistent models. How we design it, more or less, taking into account the different trade-offs and difficulties that you might encounter. And then I'm going to talk about a bit of the benefits that Scala gives you, what features of Scala are like handy to design these kind of interfaces and models that might not be part of other languages, or that Scala is like well suited for this kind of patterns. Okay, so let's go into the motivation first. This is a bit of the context for the system that I was talking about. So we are going to be getting events. In this case, is in AWS. We have a Kinesis stream that triggers a Lambda, which is the component that writes to the Dynamo database. And then we will have different services and maybe other Lambdas and other pieces of code that will read from the database. So who is familiar with DynamoDB here? Okay, a lot of people, that's good. And event sourcing as well? Great. So the main drivers for us to or the things that we will want to do, like in our solution to accomplish, will be avoid the serialization overhead, which is very typical when you have like simple models to deserialize from these document-based stores, because you don't have the flexibility of SQL, where you select specific things. You mostly get like whole documents. Simplify our domain. We got to a point where we were repeating a lot of the same patterns everywhere, so we wanted to unify and simplify the domain. And then make it easier for developers to onboard new services or new consumers for this data, and not step into each other's toes very much, right? So the first part, so I made like a quick comparison here with the SQL to explain a little bit why you will have like different overhead when reading from Dynamo. So instead of having like a well-defined schema and ability to shape the data that you're retrieving in the database itself, most of the time you have to get the full document, and then once it's deserialized, you map it to something else. And this also means that you have to design the database schema, the shape of your data in the database beforehand, or taking into account your read patterns as well as the write patterns. This is crucial to make sure that you don't have like a very difficult time when actually trying to read something and deserializing like 20 attributes to only use 2 of them. Then we have the typical verbosity of this kind of data stores, that if they don't support like SQL, right? There are an example here, a typical SQL query, where you just select 3 fields from a table called reply, and then you specify a couple of conditions. The same thing written for Dynamo with the JSON interface will be something like this, which is a lot more verbose, right? And also, as you can imagine, the real data is going to be a much more complex than this. This is a very naive and simple example. And usually, we have a lot more fields in the database itself stored that you don't need in the objects in your application. That are there only to manage like the life cycle and the logic of the data in the database, like TTLs and various other flags, like updated add or things like that. So let me give you an example of this, what I'm talking about when I say deserialization overhead. Let's say we have a user that is requesting an episode, and he wants the next episode, but the next meaning the next that makes sense for him, not exactly like the next in a fixed sequence. For example, he is up to date with the episodes, and there is a new one, but in the meantime, he was watching some other episodes that he didn't remember now how it went. So the new episode comes, and what is the next episode in this case? The direct, just the next one from the last one he was watching, or the next one from the last one he watched? So we need to take into account like user watching history and some other things that might not be directly encoded in the episode table, right? So in this case, we have to return our query for all episodes, use our sorting algorithm in memory. In this case, let's say for the sake of the example, we are only using the ID and timestamp for episode. Also, probably another field that I missed there, which is episode number. And then after sorting, we take the top one and use that to build a response. But the question is here, where are we like this? What is the overhead here in this case? So we are returning all episodes, and from Dynamo that means you are reading the whole records and deserializing them. So in this case, converting from some JSON-like representation to case classes. And that is very costly. Sorry, it didn't load here. One second. Sorry. Let me see if I can fix it quickly. So I need to connect to the internet for this to load. To the internet, yeah. But I think I can connect to my phone.
Were you on the free one here? Is that what you were using?
No, we were trying this one, but I'm connected to the phone. Let's see if it works now. Okay, perfect. Okay, sorry. So the previous example, which I cannot connect now. The previous example where I showed you this, in the end, this kind of pattern was more efficient. So we only query for a subset of the attributes, then do the sorting and selecting the episode that we want, and then we query for the full episode and use that to build a response. But this kind of thing comes with a lot of boilerplate for Dynamo. You had to write a lot of code for the serialization, deserialization, and the query itself is much more verbose, as I showed. So in the end, it's not that practical. And if you don't need the performance, you usually don't do this kind of pattern. So we wanted to support this pattern directly for the domain in general, to make this easy to do without all the boilerplate that comes with it. Which is very much related to the second point, which is the domain simplicity. So when working with this data, we need to have a certain number of attributes that are only there for the handling of the data, right? We have these events. The events can be out of order, so we need certain things like, for example, deleted at to soft delete things to make sure that we respect the proper ordering of the data, the events, and not the order they come. Other things like version updated at expired at for TTLs, or maybe things like it is visible or is test to support like certain pieces of data that are only there when the requests have certain flags, right? But all this data, or most of it, is probably not needed in your application logic. You can manage all this if you have like a wrapper around the database handling thing, and all that logic will be duplicated in all the applications consuming from your database if you don't like centralize it somehow. So for this, we are going to see later how we solve this, but the last point is making it easy to develop when you have different sub-teams or different people working on multiple services that read from the same database or from the same events of a stream of events. And in our case, our team is big. We were more than 20 people, and we were divided in 4 different squads. And all the squads manage different services, tens of them, multiple lambdas as well. And in the end, we needed to work on different features, but all those features might have to make small changes to the ingestion pipeline or the domain types. So we need to avoid interfering with each other, right? And the data ingestion is a key component, so we wanted to keep it centralized. We have one data ingestion for the domain for our whole team, and this way we don't duplicate a bunch of things that might lead to like inconsistent feature implementation in different applications. So this is more like the picture. We have multiple services and lambdas reading from the same tables. And yeah, the problem here might be related to all those attributes that I shared before, like the updated at and is visible, that kind of thing. That if we don't centralize the handling of that, we might get inconsistent implementation and a lot of code duplication. So let me show you how we solve these issues, and I'm going to show you how we separated the models for writing and the models for reading, and then we introduce a domain-specific database client. So we created a library that uses the Dynamo client and then implement all this logic. And the different applications that want to read from the tables, then they just add to this library to the build. So this is an example of simplified event. You have the event attributes, like ID, the event type, the ID of the subject, which is the entity inside data, and the event time, right? But we also have the entity itself. In this case, it's an episode. It has ID, version, episode number, name, flags, all the other attributes. So this is more or less the same thing that we want to separate, right? We have the entity for writing, which will need to have all the things that we need stored in the database. But then these are the things that the applications are really going to use, right? The attributes that are relevant for the application logic. And these are the attributes that are only relevant for the data lifecycle, the handling of the data in the database. So if we remove these attributes, we end up with a read version of the episode. This is like, you can think of this as the public API of our domain, and the write episode will be part of the private API of the domain. This also means that we have the flexibility to change these things. Maybe we want to rename them, or maybe we have a new way of storing or doing something similar, so we can add or remove this without impacting directly the consumers that will only know this episode type. But we can do this as well for the cases of where we need the optimization, right? We only need these fields. Okay, so we provide this and all the boilerplate and machinery related to this to deserialize directly from our centralized source of truth for the domain. And for each of these, we provide the different encoders or decoders. For example, for the write episode, we only need really the encoders. We don't need to write decoders for this. And more importantly, for the read version, the public types, we only need decoders. We're not going to write ever with an episode type to the database because we actually can, right? We're missing things. So this is more or less what we will do for all the types. And now let me talk about the client a little bit. So ideally, the client that we want to wrap this will filter out different, all the records based on different things, like the deleted out, soft-deleted records, non-visible records, test records. And also, we wanted to abstract the table or index, the names of the table index. And the reason why is this allows us to change the table name as well without the consumers having to care about this. We could, for example, change the schema of the table, and we need another one, so we add a V2 at the end. And we can more easily handle the transition from one table to the other in a centralized way without impacting too much the different applications. We want to provide an easy API for the common use cases, but also in case some application need it for prototyping or anything like that, we want to also allow the full query potential for the underlying client. So a way to circumvent our specific API and use directly all the features that the underlying Dynamo client provides. But for reading only. We want to limit to not allow writing to the database. And how does it look like? So the simplest example is this. We have a client, we just call the get method with the episode type parameter, and then we provide the primary key, which in this case is just the ID. And this will return an F of an episode. We can also do this. Instead of just one ID, we can provide a list of IDs, and the request will execute a batch request. But for example, for other things like queries, we can do it like this. So we have a query method that takes the type, and then you can call a specific query methods created for this type. So not every type will get all the methods. It's by channel ID is specific to episode. We can also check if something exists, and that's mostly all the functionality that we want. With these different combinations of this, we can do mostly everything that we need. But in the case where we need the full functionality of the underlying client, the apply method of the query allows you to specify like the full Dynamo query with key expression, index name, filter expression, and order. So let me go through an example, which is a test implementation. So this shows how the client can be used. And you'll notice there are some things that I didn't mention, so I'll go over them now. So first, to build our client, the domain-specific client, we need a client to talk to Dynamo. In this case, is the Java one, right? Provided by AWS. And then we create an instance of our client, but this, you can see here, we have a test version of the client. Why? Because this test version actually can actually write to the database, and only this. The regular client can't. So we also provide a lot of generators for every write model. And we are using a Scala check here to generate a bunch of different write episodes. We insert the episodes in the database, and then we do all the different things just to show what the client can do. So we check that the episode exists. We get an episode, and then we query the episode by channel ID. But if you notice, what we get back from the client, we cannot compare it directly to this episode here, because what you get back in the interface, if you remember here, is episode, not write episode. So now we have to convert one to the other. And in the end, we do this using a library that, in this case, is, I believe, duct tape. But you can do this with other libraries, or maybe even implement it yourself. But it was really useful and a key component to make this usable. To write tests, and we rely on the fact that the read version of types is always a subset of the write version. So you can always map the write version to the read version. It's just removing things. So we package this as a library, as I said, and then the different applications and the data ingestion pipeline as well depends on this client, which in turn depends on the domain types. This is kind of the shape of the modules. So what are the different trade-offs? So for the pros, we have this separation of concerns. We have different types, and I showed that we can use, or we can think of them like a public API for our domain and a private API. And it makes it easier to modify things, or to not make it explicit to not use certain fields in application code, because we reserve the right or the option to modify them and to handle them internally. Makes it easier as well to incorporate things where it's not needed for the applications, like new logic for how to store or delete things from the database. We simplify a lot the domain. We went, in these examples, which are very simplified, it's not that huge of a difference, but we went from having types with more than 40 attributes to things like 10 or 12, which is pretty neat when you have to use them in actual code, and don't have like a bunch of things that you don't even know what they're for. And this makes it much more easier to maintain and develop new things, because the domain is much more focused. But it's a lot more code. You now have at least 2 different classes for the same entity. And you don't have like a lot of duplicated code in different applications, but you end up with a new library that you have to maintain. And then you introduce a little bit of complexity in test, but I showed the example, we can like minimize it. It's not that huge of a deal. So that's mostly it. I'm going to go over now the different features of Scala that made it possible, and I'm going to show you some of the snippets from the implementation of the client to go along the different like Scala features that we used. So these are the main 3 things that I will say are interesting about Scala for our particular example of the domain and the client. Contextual abstractions, givens, you should be all familiar with it. So I'll skip the example and I'll go directly to the client example. We are using that for the decoders, but also for other things. This is more or less the shape of our client interface. You can see we have a type parameter first in the methods, and we propagate that to this kind of exist ops, whatever ops that get the type as well as the effect type. So we provide all the decoders for the types in the companion object. And this is the more or less how the example for the getops is implemented. So we also use the given, and in this case using for the configuration. But the interesting part is how the apply methods work. So this is what is allowing us to have this syntax where the type that you're specifying as a type parameter is able, the client is able to like use all the things related to the type to make the query and to select the table and all that. For this, we are using this instance of the type class table, which provides the information for the table name and partition key. And in case where the table has a sort key, it also provides the sort key. And then the more complicated example is for the query. So what the query ops class is doing is just allowing you to specify the full query with the apply method. This is the example, the last example I showed previously, where you can do whatever you want. This is the full feature set of the underlying client that you can specify. But if you remember, I'll go back to the slide where I show this. So here, you can specify, you can call another method here, right, after query. And this method is specific to the episode type. How we do this is we use extension methods for this. The interesting thing is we provide the extension methods on top of the query ops for episode. And this will be only the extension methods for episode. And the autocomplete in your editor really picks this up really well. So when you're working with it, autocomplete, you will get all the possible queries that you have for that type. The way this is implemented is you have access to this to the query interface, and you specify the parameters to apply. So in the end, all these methods are doing is just providing a shorthand of all the parameters of the query. And then obviously we use opaque types a lot. This is the is-test example. We define all our domain types without using like primitive types directly. With wrap everything with opaque types or enums or other case classes. And this is really helpful to really have like a neat domain. You don't get the chance to like swap two unrelated types around and end up with a wrong instance. And yeah, instead of having like name, for example, be a string, is an opaque type name, and so on. So to summarize, I've described our approach to read and write models and why we wanted to use them, how we separated the read and write models and different issues we encountered along the way, the trade-offs, and even some of the features that we use in Scala and how useful those features could be to implement the functionality that we wanted from our client and our domain. And that's it. Thank you.
There you go. Thank you, César, for the presentation. Hope that was insightful for you guys. Yeah, we're going to open the floor to some questions now. So if you do have questions, yeah, just raise your hand. And we'll try and get to all of you before time runs out. But,
So have you noticed how much of reduction in time for the queries to Dynamo has resulted from changing this? So once you change and you duplicated the model like writer and for writing and for reading, once now that you're using the reading one, how much have you seen that the time for Dynamo to reply those requests has decreased?
Yeah, so the example I showed, the sequence diagram, is actually from an actual case that we had an issue where querying these episodes, these full episodes, was taking around like 300 milliseconds because we have like 1,000 episodes or something like this. And after implementing this solution and a few tweaks, like for example, we also changed how we store timestamps. Instead of like a full string, we use the epoch time. We went from like close to 300 milliseconds for a request to something like 40 or something like that, 40 milliseconds. So quite a lot of impact in time.
So thanks for the presentation. It was nice. If you change the right model, how painful it is to do, like, and what does it mean for you to change the right model in this architecture?
What do you mean exactly? Change? What kind of change?
Any, like, how do you migrate the right model? If you need, like, if requirements change, if you maybe suboptimally model something in the right model, can you deal with it, like make it better, and what would it mean?
So let's say, for example, we want to add something. Adding more fields, for example, is quite easy. If you want to like really change, you change the name, you change everything about it. You can split in two attributes or something like this. Yeah. So dealing with the changes to right model is really easy because it's only one component that is using them. It's an ingestion system. In this case, it's a lambda, and you change. Say you split it into tables, right? So you will create a new model, a new right model for just the second half of the attributes. And then you start consuming that. And for the other part, you can delete the things, the attributes. I think it will be a lot of the issues or how to respond exactly will be related to how the events change rather than how we model the right classes. So the event that we receive in Kinesis. So our system in the end is mapping one event to run one dynamo write. We are not doing like aggregation or anything like that.
Any more questions? If not, I'm sure Cesar's open for you to ask him outside of the presentation. But thanks again, Cesar.
Thank you.